Hello, everyone, and thank you for joining our call today. And today we'll have a presentation on the virtual machine of ours and schema and some more technical details. So Maxim, when you're ready, feel free to start.
Thank you very much. Over the last week, I had quite a good progress with developing more advanced programming capabilities for Rgb, which I didn't expect it actually that to happen that soon. So today I would like to share these updates and bring some highlights into what it may change and what it may mean for the Rgb and its future. So the last week presentation, well, call, not even presentation, the call was about completion of the layers underneath Rgb, layers related to client-side validation. And last week we released a client-side validation library, which we believe is the final form of the library. It is fully documented, test covered, and we are quite happy with its form. So we believe that both API and binary structure of the data that this client validation is working with is final and will not change in the future, aside if we will find some bugs or there will be some problems, but we hope that it wouldn't be the case. And that is ready, and we started with working on other layers of the Rgb technology stack, targeting to finalize them as well until we will get to the top level of Lightning Network related functionality, and we will be able to say that Rgb is ready for real world testing and beginning of real world adoption. Probably we wouldn't recommend instantly issue some high value assets on it, but it clearly can be started used by reckless people the same way that happened to the Lightning Network when it was released. So it was working in production, but not recommended to use for anything that stores significant amount of value that you don't prepare to lose. So the same probably will happen to Rgb. We hope that it will happen quite soon. And the next layer we was going to work was related to single-use seals on Bitcoin blockchain. And this part of the stack we call BP, Bitcoin Protocol Core Library, which will help in the implementation of deterministic Bitcoin commitments and Bitcoin-specific part of single-use seal functionality. And we were also going to dedicate the call for explaining how the single-use seals work in general and specific on Bitcoin blockchain, because there was interest on this technology from the community, even outside of the scope of the core of Rgb, for systems like Bitcoin-based identity and other potential applications. Unfortunately, the person who has initiated this, Christopher Allen, he wasn't able to attend the call today, so we decided to move this call on the next week. The other thing that resulted in this shift from single-use seals completion on the computing part of Rgb was because with the single-use seals on Bitcoin and deterministic Bitcoin commitments, with this release, we target full support for Taproot and for Taproot-based outputs. And for that, we need a release of Rust Bitcoin, of new Rust Bitcoin library, which I've been also working on. And basically, we did a first part of Taproot support there. However, the release takes longer, and because everybody has to do a peer review, and people are just busy with other stuff, and it will take probably another week or so. So I decided to switch from the Bitcoin-specific part, which is blocked by the finalization of Taproot, to the computing part of Rgb, which is not Bitcoin related. And as I said at the beginning, I was really surprised that I was able to complete some things which I thought would require much more time. In particular, it is related to virtual machine for RGB. But probably I will start with more generic explanation. What type of computing are required by RGB style smart contracts, because there are certain shifts of paradigm, and what we actually needed to do that computing, and then doing an update about how today we have that part of the functionality implemented. So RGB is a client-side validation protocol, which we were talking a lot about this on all our calls. And it is important to remember that client-side validation is still based on certain commitment rules. So we need some global medium with a consensus. And in case of RGB, we're using a Bitcoin blockchain and Bitcoin transaction graph as that layer. And that's why we actually need the data to be part of the correct Bitcoin transactions, of the validated Bitcoin transactions. And we basically reuse the capabilities of Bitcoin protocol and Bitcoin script to define the first part of what we call RGB smart contract. And this part defines who owns certain assets, or more generically, certain contract state, because the state is always owned. For those who are not familiar with the concept of the state ownership in the RGB protocol, I invite you to watch a few presentations that we had on this topic, explaining what it means to own some certain state or to own some certain assets. And this ownership properties, the owned form of owned digital rights, is completely controlled by Bitcoin script. So basically you assign the ownership of certain digital asset to particular Bitcoin transaction output, already existing output in Bitcoin transaction. And whoever is able to spend that output with all Bitcoins on that output is actually an owner of this asset and this digital rights, because whenever he spends this output, he is able to create a state transition of the RGB smart contract and create new state, like do the transfer of the assets or execute certain form of digital rights assigned to that specific output. So we're not changing anything here, and we are very happy that we don't need to reinvent the wheel, and we are protected by the same strengths of assumptions and technology, which is already working for 10 years. Basically, it is run by Bitcoin full node, Bitcoin core, the validation of this part, and we don't need to audit it or to do something with that, because basically we are just reutilizing the underneath layer. However, that is not enough, because while you may have the right to do something, like to transfer asset that you own, you still have to do that according to certain rules. And these rules represent the client-side validated part of the logic of the smart contract. And this client-side validated part consists of two main blocks. And we use two different technologies to perform validation on that part. The first part, what we call Rgb Schema, it controls how state may be changed. So while you're doing transfer of the asset and you have the right to do that, you still have to compose a new state, assigning new owners according to certain rules. Like, for instance, when you do the transfer of the asset, you are not allowed to issue new assets at the same time. And this part is actually defines the structure of RGB smart contract. And RGB smart contract exists as a form of directed acyclic graph. And Rgb Schema defines the rules for change in the structure of this graph. We will probably dedicate a separate call for Rgb Schema, because it's very complex and quite interesting topic. I will just say a few words about it, because my initial understanding was that Rgb Schema is a very specific part of the technology which is not comparable to other existing smart contract programming techniques. So it's not a script, it's rather a declarative data structure. And I had thought that it's very limited in terms of its capabilities. However, quite recently, we understood that it is not the fact. And this, because Rgb smart contract is a directed acyclic graph, and schema defines the rule of the evolution of that graph, it turns out that declarative schema is in fact a Turing-complete functional programming language. So we will pay more time to addressing these matters and what is possible to be done with a schema. But today we will spend our presentation on the third part of the Rgb validation, which is not just the rules of how Rgb graph can evolve, but rules how the specific state may change. So if schema defines that whenever you do a transfer of the asset, you can't do an issuance of the asset at the same time, or you can't burn any asset. For that, you will need a specific dedicated state transitions composed according to their own rules. We still have the problem of validating not the graph structure, but the change in specific state assigned to certain inputs. Of a single state transition, how it matches rules like we need that the sum of all inputs equal to sum of all outputs. Or maybe somebody would like to compose deflationary asset, and they would like that with each state transition, certain amount of asset will be removed from the circulation. So for these rules, we can't define them with a declarative type of language like Rgb schema. And previously, and we need some more script-based logic. And previously, what we was doing for such things, we wrote what we called an embedded procedures, which were part of the Rgb library itself. So you can't change their logic. It's a part of the protocol. And this procedures was covering very specific cases that we had. Mostly it was a RGB20 related case where we need to control that the sum of outputs equal to sum of inputs, and few others related to NFTs. However, this is very restrictive approach, since with that you can't have external developers creating a new type of assets, for instance, deflationary assets, as in the example that I just mentioned. And we wasn't happy with that fact, actually. And we've been looking for adopting certain virtual machine that might allow us scripting, more complex form of scripting and programmable logic for Rgb in part that validates the state. Our initial expectations when we started designing the protocol was to get simplicity script. Sorry, not simplicity script, simplicity when it is completed by blockstream to be part of Rgb. Unfortunately, it took much more time than we expected. And now we are already quite close to the release of Rgb, while simplicity is still at early days of its development. And we did an analysis of what alternatives can we do. I will have additional slide about that analysis. And it happened that the only alternative that we can use is to develop our own virtual machine specific for the needs of client-side validation, which seemed to be a big challenge. And however, after the analysis and certain development efforts, we found out that it is much more simple than we originally expected. And today I would like to present the first implementation of the virtual machine for Rgb and assembly programming language that allows to program this virtual machine. But let me start with describing what is specific for client-side validated virtual machine and why we needed something which is quite different from the products and solutions that exist on the market. I would like to ask you if anybody has questions to ping in the chat or to just say out this question loud, because it's better to address them during the presentation rather than taking time after that when you don't remember what part it was related to. So let's start with the way the most of the computers, personal computers, mobile phones, and even enterprise level computers like mainframes and cloud-based computing is working today. It is not only related to central processor units, it is also related to existing virtual machines, like many of these virtual machines which you heard about, starting from WASM, and Java virtual machine, and many, many others, LLVM, and so on and so forth. They all work in a very specific model, which basically sometimes called von Neumann architecture. And I try to schematically present what it is about. Is basically we have a CPU or virtual machine which acts as a main logical unit of the program execution. This CPU has an access, random access to external memory. That's why it's called RAM, random accessible memory. It can take data from there and put the change data into that memory, and you can address that memory. And of course, you can go outside of the bounds of the available memory, which is the cause of many errors that happens on the computers. On this other side, this CPU or virtual machine interacts with other chips like input-output controlling units, which allow CPU access disk data stored in permanent memory or persistent memory, and networking environment, like using internet protocols and so on and so forth. So we have a very, very advanced environment. And the other side of this advanced and opened environment is that it's very easy to generate undeterministic exceptions, conditions under which it is unclear and undefined which specific behavior had to be followed, like maybe some networking resource is not available, or there is a disk failure, or we are trying addressing memory that shouldn't be accessed by our program, and so on and so forth. So that's why we have a lot of bugs in the modern day software, because it is the other side of the rich functionality that can be achieved with these systems. So this already exists for more than 50 years. This is what we call computing. However, there was a recent shift in the computing paradigm, which happened with the invention of, well, I wouldn't say the blockchain, I don't like the term blockchain, but let's say that invention of distributed systems based on consensus rules. And when we have a distributed system, we don't have any more input-output devices. We can't access disk. There is no such concept as a disk, or we can't access network. Why? Because blockchain by definition requires finality. And with the finality, we can't work with something that is unpredictable, like network resources. The only thing that is available for us, and we don't even have access to the local memory, to the random accessible memory. Instead, we have the only item that can be used by this virtual machine, and this item is a blockchain stored data. And we can read this data, and we can write this data. So we can create a new state on the blockchain by doing a transaction, and this is also performed with this virtual machine. The first virtual machine of this type was, of course, Bitcoin script, which was very simple and non-Turing complete, but it was still working with the same way. Unfortunately, it was also restricted, well, not unfortunately, even fortunately, it was also restricted in a way that it wasn't able to create new transactions. So it can only read the data and very specific portion of blockchain data, like previously stored public key. The first virtual machine that had all the capabilities shown on this slide was EVM, Ethereum Virtual Machine. With that, you are able to create new transactions, you are able to access the data stored in blockchain, and it is Turing complete. And still, while we have limited the amount of resources available to the system, like we don't have any input-output devices, networking access, random memory access, we have a limited blockchain access. Because of certain design flaws and overall structure, you still have a lot of undeterminism here. For instance, this virtual machine runs a stack, is a stack-based. I will be explaining a bit more later what is stack-based and registry-based virtual machines. But this virtual machine is stack-based, which also creates a lot of situations where different exceptions and undetermined behavior may happen. So, but today there is nothing else exists. And after EVM, there was more virtual machines coming after. For instance, if we had a VASM, which was created for this environment, there was a special flavor of VASM with a limited functionality, which was called eVASM, Ethereum flavored VASM, developed, for instance, by Parity Technologies, which is suitable for this environment. There are other EVM clones like KeyVM, which is a more formally verified EVM by Illinois Institute and IOHK, and ELE, a virtual machine created on the basis of KeyVM with the fuzzy advancements. But basically, they all follow the same architecture with its own limits. And this architecture, even if it would be robust and highly deterministic, is not applicable to the client-side validation world. Why? Well, because client-side validation doesn't work with the blockchain stored data. And the data are stored in the client-validated part, which has a very different structure than the blockchain. And we don't want, while we want a lot of programmability and even probably Turing completeness, in this part, we don't want to provide access to random data from blockchain or from client-validated part. The most of validation logic is defined with a schema, and we don't need to go beyond those boundaries because it will lead to the increase in undeterminism. So we required certain advancements in computing, and probably it's wrong order of slides. I already covered this topic. And what we need for client-side validation is a virtual machine that gets as a certain validation logic in form of bytecode, and it not just accessing, it can only read two things: previous state on specific state transition and the new state, which is created by this state transition. So this virtual machine is unable to create a state transition. It is unable to access random client-validated data. It has only knowledge about previous state and the new state that has been already created by certain state transition outside of this virtual machine. And this virtual machine is also register-based because it allows to significantly improve the determinism of the virtual machine work. So it is more limited and restricted version of the virtual machine that is used in the blockchain world. And it happened that when we did an analysis, an effort required to restrict VASM or EVM even for be operational under such assumptions is much more advanced. It requires more effort to restrict VASM and EVM than to create a new virtual machine dedicated for these specific needs and goals. So that's why we tried to create it, and I'm happy to say that we were quite successful. And what we ended up was a thing which we called AluVM. AluVM, coming from arithmetic logic unit. It's basically a central part of the CPU that performs actual arithmetical and other types of operations. And what our machine is capable of doing is nothing more. It is purely functional, unlike EVM and other machines, meaning that each operation can be defined as a certain mathematical function. And this operation can't modify any external state or any external memory data. It takes input and produce a single output, which is valid or not valid, like a Boolean value. It has no external state. It is extremely robust and deterministic. You can't create an exception there. There is no stack. It is register-based. There is no random memory access. There is no I/O, input-output, or any memory allocations. And if you can compile the code for this virtual machine, it always runs to a certain deterministic result. So either the data are valid against certain rules that you defined in the script, or not valid. You can't get internal cycles, and we were able to do that without any gas or requiring any sort of token or embedded economy that is commonly believed to be required to do such stuff, like get Turing complete computations, but still bounded, and the computations that can't go into eternal infinite cycles. Another very important part that is this design of virtual machine should be really easy to implement in hardware, like starting with FPGAs and probably potentially ASICs. Before moving further, I would like to do a small demo why we choose a register-based virtual machine approach and not stack-based. So how stack-based virtual machine work? They basically go from instruction to instruction. So here I have a bytecode, and I'm talking in terms of Turing machine. So this Turing machine have an execution point, and this execution point goes to instruction and reads this instruction, and depending on what instruction says, performs certain action, including jumps or whatever other operations. So for instance, with a stack-based machine, we can save certain value to stack and save another value and save another value. And each of these values may be of different types. And we may have, there is certain logical restrictions to the size of stack, but still it's really easy to create too many stack elements, leading to stack overflow, comparing to the hardware limits that you have for allocating stack data. So for instance, on a notebook, you will have one requirement. If you will do the same stack on Ledger or any hardware small device, you will have much more restricted requirements. And with a stack-based virtual machine, it's hard to predict under which conditions the machine will fail because of the resource problems. This one of the indeterminism, and certain machines like ELE and KVM, they try to address that issue by defining that stack can't be larger than certain size, but still you can store different forms of data in different stack elements, and when you're reading those data back, it's hard to predict which type of the data you will get, and that is another source of indeterminism. So instead of that, we flavored register-based machines, which are usually used for hardware processors, because in hardware it's really hard to create a dynamic stack. You can define a stack as a part of the data that's stored in the random accessible memory or cache data, but these things are not part of the arithmetical logical unit. Instead, with the registers, you basically can save the data not to arbitrary stack, but to a well-defined registers of certain well-defined data type. And the set of these registers is predefined, can be extended. And you're always able to make sure that the data fit into, you are able to run this program on any kind of hardware with any sorts of limitations of the hardware. So that's what we selected for AluVM. And I will probably switch to the demo part. This machine and its implementation is just finished today, and I will be publishing the first version of it for everybody to play. You already may find the code on the GitHub. I was giving a link in the reference here. It is internet2.org Allure. which is runtime environment for AluVM. And but I will just run through some code and demonstrate how it works and looks in practice. I have one example here, and this is actually an assembly code of this AluVM. It doesn't do anything specific. It's more like testing of different forms of instructions that we have here with the different registers. So if we will look into the types of registers, we have here, we have a set of registers, arithmetic registers of different sizing from 8-bit to 512 bits, non-arithmetic registers which are used for elliptic curve operations or hashing operations, also of different size from 128 bits to 8192 bits for future more advanced hashes or key-based asymmetric key-based cryptography. We have a string-based registers, and all of them have a predefined length. And we have some operation flow control registers. Important point to note that how we were able to get to solve the problem of infinite cycles while still maintaining and Turing completeness is that we introduced a special register called cycle counter. And this cycle counter is a 16-bit register, meaning that you may have its value may grow up to 65 something, 65,000 something, and not more. And this register is incremented each time you do a jump in the code, either cycle or calling external function or returning from a function. So you are limited to this number of operations. And once you reach this limit, you'll complete the program execution specifying that the client-side validation has failed, meaning that the data are invalid. So basically, if you're unable to describe the script, design the script that can complete under restricted amount of time, you are basically creating invalid smart contract, which fails the client-side validation. And each of these registers is an option, meaning that they are started not with zeros, but in a special uninitialized state. And if you try to perform any form of operation that leads to a deterministic result, like zero division, instead of creating exception, what we do is we put the destination register into uninitialized state, and that allows us to avoid most of the exceptions that may happen during the runtime and still do not fail in unpredictable parts of the program, the actual validation process. So this is the set of registers we are operating on. And with this assembly code, we do a different, if somebody of you used assembly, you will already recognize certain parts of this stuff, moving values, doing arithmetical operations, doing modular divisions, and overall set of instructions. There are 256 possible instructions. Each byte is a valid instruction, in fact. And most of these instructions are split into families like control flow operations, register value manipulation, moving the values, comparing, arithmetics, Boolean logic, operations on byte strings, cryptographic hashing functions, which are supported natively by this virtual machine, operations on two of elliptic curves. We plan to add more elliptic curves later, and extension operations, which are provided to the runtime environment by a host environment. In our case, the host environment will be Rgb, and these operations will cover access to the previous and new state data to load them into the registers for further validation, and not an operation. So this is a set of instructions. All of them have a corresponding mnemonic which you can use. And another point I would like to address and bring your attention to is that for all arithmetic operations, we have 8 variants of each operation, performing a checked operation. Like if you overflow with addition or multiplication, the checked operation will lead to the fact that the destination register will be brought into uninitialized state. Or unchecked operation variant, which will, instead of bringing destination register into an initialized state, it will overflow and just basically do a modulo the maximum value, and you still will get a result which will be a shortened version of the actual result. There are also arbitrary precision form of operations that uses arbitrary precision registers, meaning that you can do arithmetics with arbitrary precision, float variants for the operations, signed variants for the operations, and so on and so forth. So we have this assembly, and if we will run a demo program here, we will see that this demo program, what it does is it takes this assembly, compiles it, and produce a dynamic set of instructions, and we print these instructions out, which we see from here, and also serializes these instructions into a bytecode. And this bytecode will be a part of the Rgb client-side validated data. It will be embedded into Rgb schema. For each specific type of the state, you will have this sort string of the bytecode. And then when this bytecode read, it is back deserialized into the instructions and assembly. So we have all the compilers and serialization working, as well as program execution based on that register machine. So this week we will complete test coverage of the whole code base for virtual machine, and we will be happy to have this AluVM a part of the Rgb as it will be released in its next version. So happily, we are happy that we were able to close this tick box of Rgb having a dedicated virtual machine for state validation. So regarding the virtual machine, we have AluVM, which is actual specification of the virtual machine, and we have a implementation of it, which we call AluRP, which is AluVM runtime environment written in Rust. And this runtime environment will be integrated into Rgb. The next thing we will integrate it into Rgb core library next week, and it will be called from the core library. The interesting part that the whole implementation of AluVM is less than 10,000 lines of code. So it's really easy to audit. It is already fully documented as a doc comments, and everybody is welcome to look into it and find issues or bugs, because there might be some at the early stages, but we believe that we will be able to quite quickly stabilize this functionality. And we were able to fit it into this small size because of all the restrictions that we put with the client-side validation. We don't have random memory access, blockchain data access, creation of a new state transitions. We don't have the gas and other stuff that is usually used by the virtual machines. And because of that, the thing that we were not using stack, and I do believe we were able to design something that will be really robust in these terms. Finally, I was already showing this slide when I was discussing on previous calls the idea of the need in the dedicated virtual machine for Rgb, and we were able to do better than we expected. So these are still the same options with AluVM added. And we see that we have a very good set of trade-offs, maybe not perfect in each point of comparison, because the best solution shown is in green, the worst in red, and the second best is in cyan. So still, the whole combination of the factors that were considered is very beneficial, even comparing to simplicity, which is more audible because you can do a formal verification of simplicity script with the mathematics, and probably more safe because of that. But in all other respects, we have better properties. Of course, it will be harder to develop advanced scripts using assembly language. So later on, we will be finalizing what we call contractum language, which can be used to define both Rgb schema and the scripts for AluVM. But we are happy that we don't require it to complete it before Rgb release, because this is just a language which will compile into AluVM bytecode, and we can complete it after the release of Rgb as a part of the overall tool chain for Rgb developers. There is also one thing I would like to share with you regarding how AluVM works with the libraries and how it is structured. I'd also like to get your feedback on that, but probably I don't have specific slides for that part, and probably we should have a question and answer section before moving to this final part of our today's call.
Perfect. Thank you very much for the presentation, Maxim. So you can see the comments on the chat. So
yeah, I'm reading them right now.
Yeah, so the first comment is arbitrary precision data and strings causes the need for memory allocations. It also will make way more difficulty for FPGA implementations than, let's say stack.
Just a second. Let's go question by question, because I wouldn't be able to answer two of them at the same time. So the first question, I'm trying to find it. I don't see it.
There are no open questions right now. There are just comments.
Okay, so the first question that you mentioned was the need of allocation, how we avoid that. We avoid that with the fact that no piece of data may be larger than 16-bit sized addressable string. So the largest piece of data is 64 kilobytes. And this happens for arbitrary precision arithmetics and for string values. Because with the client-side, this virtual machine is designed for client-side validated data. And one of the rules of the client-side validated data that may not exist data larger than 65 kilobytes or 65,000 of items. And because of that, we can limit the virtual machine capabilities. And basically, 65 kilobytes is a very small amount, even for embedded devices and for hardware wallets. So thus, the largest size of our register is 64 kilobytes. And that's why we don't need any allocation at all. And the current Rust implementation of AluVM, unless you need to compile the assembly into the bytecode. But to run bytecode, you can run it in most STD environment, meaning without any standard libraries of Rust being used and without any allocator at all. So that's on the allocation part. The second part is can you please ask that question again? Repeat that question again. Olga.
Yes.
You was asking the second question after the memory allocation, and I forgot what it was.
Again, there were I don't see any questions. I see only comments.
But you said that you asked the question. I don't know where you read it.
In the chat.
Can you read it once again, please?
Guys, if you have any questions, you can ask them right now, because for now I can see the comment that 64K is rather big size for a register. Maxim, if you want to comment on that. You can do.
Well, it's a big size for hardware register. And I have to emphasize that this virtual machine was not specifically designed as a hardware device. It was designed for the need of client-side validation, and by default, it runs as a virtual environment, meaning that not directly executing on the hardware. So there is a virtualization layer, and that's more than enough. The 64 kilobytes is not big for that. However, I assume I'm not a good hardware designer, but I assume that with the modern day technologies, it's not hard to get 64 kilobytes to be a part of some ASIC or FPGA, because the size of cache data, for instance, used inside the modern processors are counted with megabytes. And I doubt that probably it would be a big challenge for hardware designers, but maybe I'm wrong in that part. So if you think that this is a challenge, then it is.
Also, I have a feeling that you have a wide range of types and register sizes, and that makes things a little bit complicated. I'm not sure if brings a lot of value of having all of those, like 15 types of registers and types and sizes and so
on. You mean for hardware implementation, or which kind of implementation?
For assembly language, because then you basically need to allocate space in the bytecode for each type, right?
Not exactly. So if I will share the screen once again and show how it looks like in the code. So basically, each instruction defined by a single byte of the code. And this instruction may operate on a specific set of registers, like addition or arithmetic. Any arithmetic operation will use only arithmetical set of registers, or hashing operation and elliptic curve operations will use a set of registers related to non-arithmetic operations, which start with the R index. So here we have this one set and the other set. And why we have two different sets, not a single set, because they have a very different bit dimensionality, and also to prevent things like there is no point of doing arithmetic operations on hash values because it's meaningless. And when you do a sort of modular arithmetics on elliptic curves case, it's a different form of arithmetics than the normal arithmetics of the integers and float numbers. So we are separating these two sets of registers, but still the specific comments, they're dedicated to a single type of registers by definition, and that's why we are not increasing the size of the instruction. The second, there are some certain comments like move operations, which allow you to move values between these two sets of registers. But the way it is structured is that any instruction, aside from operations putting a certain string into the string register, because it may take longer, the value of the string just given in the plain code, but all other operations are feeding into less than 4 bytes. So it's either single byte, 2 byte, or 3 bytes, which is most of the commons, or 4 bytes. Common plus it's all operands covering the destination set of registers. So we have 32 type of registers in each block, which allows us to code the type of register, the bit dimensionality of the register with just 3 bits. We have 32 registers in array, which allows us to encode the index of specific register used with the 5 bits. And this single register is encoded with a single byte always. If we allow instructions to operate on both dimensions of registers, both families, we either do that with the 2 different instructions, so we use the same mnemonic, but in fact, that becomes, let me open the actual implementation of instruction. So we have one instruction operating on A set of registers and another instruction operating on R set of registers. And if we have operations between these two families, we have also a dedicated operator. So we still fit, because we have up to 256 instructions. Today we are using just a little bit more than 60 instructions. So everything fits, and I wouldn't say that there was big challenge in designing the set of operations with that amount of registers. So it can be reduced further. For instance, I'm not sure that we need 32 registers of a single type, but if I will use just 16 or 8 of them, we will have extra bits, and we wouldn't be able to, we still will have to align the operations on the byte boundaries, but we wouldn't be able to do that, and that will introduce indeterminism because certain bits wouldn't have meaning. And that's why I ended up with this particular design with that amount of registers, type of registers, and amount of registers inside an array for a specific given type.
I mean, actually, having non-used bits does not make it undeterministic. They're just ignored.
It is not making it undeterministic. Yes, you may ignore that, but for me, it looks like a more poor design. So why we need that? Maybe the only argument I may see is the hardware limitations and implementation cost in the hardware of a such virtual machine. Yes, but I'm not expert in that, and I probably would be happy if somebody of you can suggest, well, I need some expertise on which specific amount of register today with modern day processor designing technologies is desirable. And if it will be less than what we have, we may still restrict it, and we'll have a special version for hardware. We will just create a restricted version of this environment to fit into hardware. So you think it's too much of it. So if your argument is that it will blot the assembly and bytecode, no, I was able not to blot it. If the argument is that it will be really hard to do for an ASIC or FPGA, that's another case, and then in that case we probably need to restrict it.
Yeah, I was mostly talking about basic hardware implementation and how you would do it in FPGA, let's say, or something like that. But I guess we can put this conversation maybe sometimes offline. We don't need to have a full-blown discussion on that topic right now. Another point which I believe is also important, or rather important for determinism, is the floating point. And basically, in that case, you either need to really specify the whole floating point operations and implement each floating point operation in Rust or whatever, so that would be a little bit painful, because basically if you leave it to the processor or to the compiler, you end up with whatever implementation or hardware implementation of the processor you get, and that is not always very deterministic, and I wouldn't rely on that. So floating point is kind of tricky to get proper right and deterministic. So
that is correct, and this is a big pain for many environments like blockchain or machine learning, because it's really hard to get machine learning training deterministic because of that. I haven't completed the part for floating point yet, but what I found out that there is a good library, a low-level non-STD library designed for arbitrary precision floating point operations. And we basically will use it for any floating operations. Just for non-arbitrary precision, we will shorten the result to fit into the float register, 32 or 64 byte bit float register, or we will maintain the full value for arbitrary precision operations on floats. So yeah, the float wouldn't be performed by the processor capabilities, but using this arbitrary precision arithmetics on floats in Rust.
Yeah, but then you basically then you will have real pain in having it in hardware, because then it would really require a lot of resources, I believe.
It is true, but it is also true that for such type of applications, you may not. If you will design something in hardware without with this floating point problematics, it wouldn't work. So we will just need to probably, when we will come to the point, because I do believe that it will take years to design something for this virtual machine in hardware, and the part of this process will be to standardize floating point arithmetic such that it will in fact represent the same logic as is done by the arbitrary precision float arithmetics, but in a shortened version. So the actual hardware implementation wouldn't do precise arithmetics, high precision arithmetic, arbitrary precision arithmetics. It will follow a certain standard that we will have to develop, and this standard should match the result which we get with arbitrary precision float arithmetics. Not sure that I was able to explain the idea.
No, I think I understand. The thing is that there is also a standard which is already in use for floating point. I think the IEEE 7.3 something, where it's precisely specified how the system should behave in case of floating point. And most processors should be actually using it and implementing that standard. But then again,
why they are undeterministic in this case?
But then still, like there are a lot of corner cases, and the question is if the hardware implementer actually really took care to be very precise in the implementation, and in general, just working with a floating point brings a lot of tricky calculations just from the algorithmic point of view. So having deterministic execution with floating point is somewhat tricky, to say the least.
Yeah, that's true. For the first part that you said, that as far as I know, EEE standard, it allows certain antideterminism and certain. This sum of the floating point problems comes not only from hardware producers not precisely following the standard, but because the standard by itself allows certain forms of indeterminism. And maybe I'm wrong. I'm not expert in this area, but from what I was reading, it looks like that. So probably we will need another standard. The other option, well, we can avoid floating point arithmetics because really I don't see a lot of its use for of floating point arithmetics for Rgb type of smart contracts, because all the amounts of tokens, for instance, they are always defined as integers, and for any sort of financial operation, we need to use integers for accounting, just by putting them this floating point for the user interface, but internally keeping the value as an integer. So probably 99.5% of Rgb or any thinkable Rgb smart contracts wouldn't require floating point. So we can just remove that set of operation. If we do believe that it creates a lot of headache but doesn't add value.
Three-Call, you also had a question, I think. You raised your hand.
Yes, I had a question. You were telling that the registered language that you use to make your instructions was purely functional. Can you?
No, not the language. No,
Okay.
that's different things. The virtual machine operates as a functional virtual machine, but the assembly language, of course, it's an assembly language. It is not the functional language. So there is difference between functional virtual machine and functional language. And what I was naming functional language is not an assembly language for virtual machine, but Rgb Schema, which is not related to this virtual machine. So there are three different entities, and the relation is different.
Okay.
Sorry for confusing with that. So Rgb Schema is defined as a functional language because it's a declarative language. It's even sub-family of functional languages. It's a declarative language. The AluVM is a functional virtual machine. And right now, we have just a single language, which is assembly language for AluVM. And as any assembly language, it's a bytecode-based language. It's neither functional nor imperative.
And a second question, could you imagine that you could compose two VM together? For example, if you have like state 0 that is checking state 0 and state 1, and you could maybe have also a second VM that takes state 1 and state 2 and compose it into another VM that would just take state 0 and state 2?
Well, while of course you can do something like that, I don't see why we should do that as a part of RGB. So AluVM is not equal to RGB. So AluVM is a virtual machine that may be used outside of the RGB. And when RGB, so we have a hierarchy of three things. So there is AluVM as a standard and specification that we'd like to define that says that we may have register-based functional virtual machine with these properties, this instruction set, and that's on, that's all. There is a specific runtime environment that implements virtual machine and allows to work with such concept as software libraries and so on and so forth. So that's another layer on top of that. But it can be, there is a third layer, which I call a host environment. It's actually a system that takes this runtime environment and applies to a specific case. So RGB will be a host environment that takes Alu runtime environment and extends it with the commands accessing the state data. And in this case, inside RGB, this AluVM will be isolated from all the state other than previous state and the new state defined by a specific state transition. And even within that state, it will be restricted to a single type of state. So it wouldn't be able to cross-validate different forms of state because of the safety concerns. And in fact, all possible applications of RGB we were thinking about is possible to do without operating multiple forms of state. So we deliberately restricting access to state data by the virtual machine. But nothing prevents you from creating some other non-RGB host environment and use this AluVM in different way and even compose virtual machines over virtual machines. That's why we have extension codes for operations which are provided by the host environment.
I have a question.
Yeah.
Does the virtual machine only operate on RGB tokens, or can you send sats to it?
No, virtual machine have no concept of a token, and it doesn't operate on RGB tokens at all. It operates on the integers and values, and it has no internal concept of what is behind those values. So it will be up to the smart contract developer to use this virtual machine to validate tokens or something else.
Does that mean that you can, it sounds like you can write a contract that accesses the virtual machine to do a task, and then you have the option of involving tokens in that. Am I on the right track, or am I still off base?
I'm not sure that this can be put this way. So the token is whatever you name token. Token can be anything. It can be fungible, non-fungible. And as a developer of smart contract, you define what is token. So for me, if you're asking, can virtual machine have access to tokens? It depends on, well, it can have access to anything that you give access to. And the token is whatever you name token. So I just can't compile the question.
Right. I think let me try and rephrase it. Suppose that I wanted to use the virtual machine to create a piggy bank where I can send tokens in to the virtual machine and then later withdraw them. Is that
you can't send anything to the virtual machine. Virtual machine does just the validation part. So you can send with RGB. You can send something only, actually not send, but assign something to specific Bitcoin UTXO, and virtual machine has no knowledge about UTXOs and Bitcoin blockchain.
But could you do something where you assign tokens to a UTXO and they can only be withdrawn from that UTXO if parameters are, or if certain state is
correct? Yeah, you can do that. That's how it works.
So then if I wanted to make a piggy bank thing, I could say like I assume I would need to write something where the virtual machine would be able to check are there X amount of tokens associated with the UTXO, and if there are, then you can withdraw, otherwise you cannot. Is that something the virtual machine can be used for?
Correct. I don't know what piggy bank means, but what you have described, you can do that.
A piggy bank is a thing in U.S. culture where you give a kid like you give a kid a jar that is typically shaped like a pig, and he can put things in it, and then after it gets full, he can open it and get them out.
You can do that stuff. Yeah, you can do that stuff with RGB, and virtual machine will be part of that validation logic. The code executed on virtual machine will be part of that validation logic, but you have to write the code by yourself, and you can program something that if the amount of tokens is less than certain limit, then the operation fails.
And does that require a new schema, or does it not matter what schema you use?
It will require a new schema. What we were thinking about, it's a bit tricky because nothing prevents us from doing some schema that allows arbitrary scripting. This is possible with RGB. But while we are not doing that with RGB20, which is thought to be a common schema for tokens on RGB, is because that will allow to create certain validation logic which is scammy or failed by design, because we allow arbitrary scripting. And people will certainly create not only piggy banks, but they will also create tokens that just disappear in random manner or whatever. And people wouldn't be able to distinguish those from the user interface because they will see that this is RGB20 standards and they will probably trust to it. And that's why we think that the approach when RGB20 will be related only for like just normal tokens without any additional advanced scripting. And if somebody needs something more advanced than just normal rules like sum of inputs equals to the sum of outputs, they have to design their own schema, and people will see that it's not RGB20, but some other type of schema, which may have different behavior from what they expect from RGB20. So it's purely social engineering considerations, not technical.
The piggy bank example is of course is just an example. I don't particularly care about that contract, but I'm going to keep using it for a moment. I was talking about this with Olga last week, or in the Telegram chat, about the concept of making a schema that would allow for some kind of piggy bank contract, and I came away with the impression that contracts like that, or contracts that haven't already been thought of and programmed into RGB so that it can recognize them, are not doable. Because if you try to use a schema that's not already been programmed into RGB, it's not going to recognize it, and nothing's going to happen. Is that accurate, or what's your question or to those thoughts?
Not exactly. RGB can work with any schema. It was that just before this week, you can't do a schema with advanced programmed logic because you hadn't a virtual machine there, and you had very restricted set of embedded validation rules. But now, when we introduce this virtual machine, you will be able just to copy the RGB20 schema, insert the custom script into it, and you will have a piggy bank, and it will be recognized by any RGB-enabled device. But of course, it will show you as a user, it will notify the user that you accept a token under the schema that is not known for us, so we can't guarantee how it works. Unless, as a developer, you will contact the wallet developers and they will accept your schema proposal as a common known thing, like it happened to other ERC schemas. Yeah.
The impression I get from that is, yes, you can make your piggy bank, but you're going to have to create a new schema, and you're not going to be able to use existing RGB tokens. You're going to have to create a new token with a new schema, and then you can use that token with your piggy bank, but not others. Is any of that accurate, or am I?
That is accurate, but the truth is that you can't define a piggy bank for a token not issued by you. So anyway, even if you will do a different form of schema, because it is the issuer who defines the rules how a token may behave. And if you need to do a piggy bank with some other token, you have to, like, you can't restrict token with more rules than issuer has restricted it. You see the idea?
Yeah, that just
it's a
seems
security
like,
consideration, because otherwise you can have a confiscability property. You instantly get a ability for third parties to confiscate your assets. This is actually a vulnerability.
yeah,
This functionality, because the same with Ethereum, like you can't send certain tokens on some contract that wouldn't be able to release it. So if you can create a signature to create a transaction, you can use that token. So if you can create a signature to spend Bitcoin output, you can use tokens on that output.
when on Ethereum, if I wanted to do a piggy bank contract, I could write it in such a way that you could send Ethereum or Ether tokens, or you could send ERC20 tokens to it, and then only the person who sent them would be able to withdraw them after they accumulate to a certain amount. It sounds like that's going to be possible in RGB, but only with the token that is specified in the contract. Like you have to specify this token, which I have just created, is the one that can be used with this piggy bank. You can't just send any RGB token or sats to it.
I need to think more about that design. I'm not ready to say that that is the only way how you can do it in RGB. I assume that there is actually a way how you can do that even at Bitcoin level, but I need more time to think about that. So
yeah, I think piggy bank contracts are possible with Bitcoin script using one of the SIG hashes.
Yeah.
But I was
so
thinking.
If you can do that in Bitcoin script, you don't need RGB to do that. You just do that with Bitcoin script, and it will work for any token stored to that UTXO.
Yeah, that's a good point. Now I need to come up with another example of something that you can't do in Bitcoin script. I hadn't considered that you actually can do a piggy bank in Bitcoin script. But. All right, cool. Well, thank you.
Yeah, you're welcome. Interesting question. One last thing. Yeah, go on.
Tricola had another question. Go ahead.
Would it be possible to use something like LLVM, for example, to compile? Okay.
I do believe that it wouldn't be a big challenge to develop a cross compiler that will take LLVM code and generate AluVM bytecode, with the only limitation that certain operations which are valid and possible operations in LLVM will not have a match in AluVM. So not any LLVM code may be compiled into AluVM, because, for instance, if you will write some program accessing disk or doing a random memory access, compile that SIG program or ASCII program into LLVM intermediate code, you wouldn't be able to run that on AluVM, of course. because it's basically functionality that by definition is absent in AluVM. It's the same like you can't take any WASM program and run it in parity blockchain, because certain instructions are not supported by blockchain by definition. So basically, this, whatever applies to WASM being transformed into eWASM for blockchain, it's the same logic that applied to LLVM being transformed into AluVM bytecode. So there will be certain extra instructions which are, if present in the LLVM code, it wouldn't compile because of the functionality restrictions. But generally, I do believe that it wouldn't be a big challenge to design a restricted version of Rust language. Just fork the language and remove everything that has relation, remove standard library, remove everything that is related to random memory access, and you will be able to compile that into AluVM, and it wouldn't be a big effort to do that, or do that for other languages.
Maybe some time of type-saved subset of pure arithmetic and OCaml or something.
Maybe. I would like to see somebody playing with that, because literally I wouldn't have time for these experiments for a long time from now. I need to compile to complete other stuff. But if somebody would like to try to play with this, I will be happy to assist and provide some.
Basically, the main problem you would have if you try to do that is that you won't be able to have any functional call or any local variable in the function call. So you either have only global variables or you don't have functions, because you don't have a stack.
You're not limited by that. You're limited by the fact you can't use heap memory, so you can't use allocations. But of course, you can have local variables.
No, you cannot.
You will still use registers for doing local variables.
No, but then you cannot call functions from each other. So basically,
you can.
Yeah, but
you have jumps call. You can have a call stack.
But then you have very limited number of variables. I mean, basically, you have 30 variables for the whole program. That's it, and you cannot call the function from itself. You cannot have recursive calls.
No, you have 32 variables of each type, and you have 33 types of variables, taking into account that one of those types is a string variables, which you can, if you use some advanced logic, you can basically use that storage to store non-script variables as well. Because there are instructions of putting the value from a arithmetic register into certain byte position within the string register and back. So basically you have this additional amount of memory, which depending on the type of variable you will be basing on, would it be 8-bit variables or 64-bit variables, will result you of having like about 1,000 or several thousand of variables that can be defined at local and global level, which probably is enough for most of the programs. It will be just required to write some specific compiler that will be able to process that logic into a correct bytecode and set of instructions. So like certain variables, using certain variables will result in like 10 instructions to work with them if you will have a lot of variables at the end of the day. But the point that if you use AluVM for working with RGB, you are limited with the previous state data. You can't take the data from nowhere. And if you're talking something about token-based contracts, the only data you have is amount of tokens. Okay, you may have different sets of tokens, but still, it's really hard to imagine some very complex program requiring like hundreds of local variables.
I mean, basically, you're presented with a choice. You either design your own language, you would need to create a compiler to, or everybody writes everything in assembly language, or use a general purpose language, and then you try to emulate the von Neumann model of processing with stack at least and some memory. So either of the
we
three?
have the plan. Additionally to these options, we have a plan for a contractum language, which will be probably default language for RGB, and it covers both declarative part of schema and scripting part. We have online examples, so you can check how it may look like. It's in the RGB org organization contractum lang repository. So we will finalize its development, but after RGB release. So you have three options. You can write assembly code. You can, which is the only option for today. Then we will when we will finalize the contractum, you can use contractum language, which is quite simple. And the third option that you can fork certain existing language and restrict its functionality, but it's actually the same amount of options you have for any blockchain-based smart contracts. So the same for Ethereum, the same for Cardano, for instance.
Yeah, I agreed. I mean, basically all of them went with the path of defining their own language, their own execution environment, and then building their own compiler for this language. I mean,
yeah. I just believe that probably the perfect solution, the best solution for such thing as AluVM wouldn't be a Rust or C-based language, but rather it would be something like Haskell-based, which would be easier to compile into AluVM type of environment requirements.
Julian, what is COQ? Maxim, do you know what is COQ is?
COQ? No.
Yes, the language.
Yes, COQ, of course. Yeah, it's a formal provable language. It's language of formal proofs. So what is the question related for COQ? Let me check the chat. Using COQ for writing code. Unfortunately, I don't have a lot of experience with COQ, so I don't know. Maybe it can be used or maybe not.
I have yet another question. I'm really interested about this virtual machine thing. So what is the model of input and output? Do you have kind of arbitrary size of data? So can you define a schema?
There is no input and output. So basically, the only thing that you have is when you use this AluVM inside RGB, the only thing that you have is the previous and current state data. And you can't create any output. So the only output you end up is the value stored in the registers at the end of the program execution. And it's up to the host environment to use them in a certain way. So, but if you'd like to use this virtual machine outside of the RGB or some other applications, because nothing actually prevents it for using for normal computing or for anything, I'm not sure that it has a value there because it was designed for other purposes, but theoretically nothing prevents you from creating a host environment which may even access memory or something and develop a set of instructions extending the set of instructions that we had that will allow to use this virtual machine in other forms of computing. But I doubt that it makes sense because the whole point was to create something specifically for client-side validation needs.
And is it input state? I mean, what is the format of the states? Does it include like arbitrary size, arbitrary type of data, or it's very fixed, only certain? I mean, can you define schema with kind of anything?
The form of state present in RGB is defined by Rgb schema. So there are literally, it's very similar to the state registers that we have in our AluVM. Additionally to integers, floats of different bit size, it allows also to store the hashes, public, private keys, signature, which is just a set of keys as well. And well, you can store more complex data like transactions, Bitcoin transactions, serialized formats of Bitcoin transactions. But again, it's just a byte array. And because everything in RGB is a part of client-side validation world, everything also related, limited and restricted by this 65 kilobyte size limit. And whatever you store in the RGB state will always fit into one of the registers of AluVM. So basically, to access that state, what you do is you set that which type of state you're accessing, and type of state is 16-bit integer always. You specify which set of the, so because there might be a multiple state of the same type, you set from starting from which index to which index you would like to access the state, and it will copy it to appropriate register of the same type into AluVM, after which you can process it with a normal arithmetics or whatever, even string operation. So you can even process with serialized Bitcoin transaction stored inside RGB client-side validated data. But for that reason, you will need to work on the transaction as serialized by string, which is also not that hard to do. And we plan, that brings us to the question of libraries. So can you create some libraries for RGB with this AluVM? And the answer is yes. So you can write, for instance, an implementation of Schnorr signatures, running validation or creation, running on AluVM, and set it as a library. Or you can create a library that will process the serialized Bitcoin transaction data inside the string register taken from RGB code. And this library may be used by different contracts on RGB. How it works? Well, basically, each library is identified by a hash of its code. So when you call the function of some certain library, you provide the hash of the code of that library. And by that, you uniquely define which code you are calling, and you commit actually to the logic of that code. So it goes very in line with all the validation process of the script. It preserves all the safety properties. And then you specify the offset inside that library where to start the execution to. And then library can return back, and you will just know which processors are modified by the code and use that as a result of the validation by that function of some other library. The other thing is that each piece of code, each library, like let's say that runtime environment operates with a set of libraries, and each library, the length of the code can't exceed 65 kilobytes once again. So you always address any point of any other library with the hash of the library and 16-bit offset from its beginning. And when you supply the RGB contract, all the libraries used by the validation logic of that contract always are included into the consignment. So execution environment always has access to those data. And however, when you store this consignment locally as a part of the RGB stash, you don't need to store multiple copies of the same libraries. You will just store it once and use it for all contracts that are dependent on that logic.
Sounds very nice. I mean, I really like this library concept, and I absolutely love the idea of counting cycles by calls. So then you have actually pretty big freedom of executing almost arbitrary code, still kind of being limited to a certain bounds of like maybe a couple of seconds to execute it, and that's it. And it's better than Ethereum model, actually, which is overcomplicated and yeah, more free.
I don't know. I have a doubt that they probably invented the gas not because it was hard to use the counter like I do, rather than they needed some reason for creating Ethereum token.
No, actually, it is very similar. They just count every instruction. Other than that, it's very similar to your model. And
yeah, but they count every instruction, which I was thinking also about counting instructions. However, I think it's really hard to define, because first of all, we are not in blockchain world. In blockchain world, each node must validate all the produced scripts and code for the whole world, which of course, each instruction counts, otherwise the whole world forever have to revalidate that. In the client side, you're just validating only the data that you own. So you have much less amount of data to run with. The second, it's really hard to define the value of each instruction, how long it is, or how it's hard to execute it. And I thought that it's more important to just count jumps than to count each instruction, because if you do the same instruction 600 or 6,000 of times, it is more important than the differences between the time it takes to execute one instruction or another instruction. So it's like the jumps which are really important. It's a first order of importance, while the rest, the difference of the time required to execute one command or another, is a second or third or fourth order of importance, and you just simply ignore that.
Well, I would say that maybe some cryptographic operations may be also expensive. So if you calculate hashes or you do elliptic curves operations, signatures and stuff like that, that would also be challenging in taxing on processors. So maybe you would need to count those, because I'm not sure, I didn't read it.
It might be, yes. It might be that operations on non-arithmetical registers may worth 10 times than the operations on the arithmetical registers. But here we are restricting the amount. So the worst case scenario is that you have all the instructions operating the most expensive operation, doing the same operation, and you have 60, and that takes all the 64 kilobytes of the script data, and you run that in cycle. And that is the worst case scenario. It would be interesting to check what would be the benchmark of that.
Yeah, that would be really bad. I mean, 16 by 16 is 32. So it's about 4 million operations, and 4 million hashes will take several days to complete.
4 million hashes several days?
Yes,
no, it's just less than a second. For elliptic curve operations, it could be, but the point that to run this operation on the commands, the size of the command and the instruction data to do this sort of operations is quite large. So you can't have 64,000 of them. It will be at least 5 times less. And but yes, it will be nice to do benchmarking, the worst case scenarios. Maybe we need to restrict it further. So nothing requires us from having less than 64K of jumps. We can limit this number down, but I don't know. It's probably more about up to doing a specific benchmarking.
Yeah, I mean, in general, just having non-arithmetic, well, actually, cryptographic operations in itself, they are kind of expensive to calculate. And that's why you have also hardware accelerators and so on. But in general, implementing those, especially if they are software implemented, it is several orders of magnitude slower than normal arithmetic operation.
Yeah, that's true. But also, we are not re-implementing them. We're using libsecp library, which is probably the best thing to use. We also support the second elliptic curve, which is Edwards curve 25519, which is widely used for other purposes. And yes, these operations are still quite slow, and probably it's a good point to do the actual benchmarking. And maybe introduce another thing which we need to control, like amount of operations, cryptographic operations we are running. So good point.
Thank you for your answers. And all in all, it's amazing design. I really love all the implementation aspects and approach.
Thank you. Thank you. So it's been mostly 2 hours. Probably it's time to finish the call.
Yeah, it's been 2 hours almost. So, guys, if you have any questions, you can put them in the chat or speak right now. If not, we can wrap this up and talk to you next week.
Yeah. Thank you, everybody, for joining and commenting and discussing.
Thank you, Maxim, for the presentation, and thank you guys for being here over all this time. If you have any questions, you can use the Rgb Telegram chat or write direct message to me. And of course, remember that we do have a YouTube channel and Rgb FAQ website and Telegram channel and many, many other information and resources. So feel free to check that out. And if you do have any questions, as I said, feel free to drop them. Thanks again. Have a great day. Talk to you next week, guys.
Bye-bye.
Thanks, guys. We'll see you.
Bye.
Thank you. Bye.